You remember this program or this example that we did near the end, right? It came from the second example. So let me go back to the three examples that we looked at, right? The first one has an iteration space 2D, that is 2D, and the data space was also 2D. And really, if you look carefully at it, any element Aij is written into by this program fragment exactly once. So sometimes such codes are called single assignment codes because you do only one assignment to any memory location. Such codes, if you think about it, are horrendously inefficient. Why? Because the number of iterations is equal to number of data values, and you have been studying for now a long time that memory accesses are more expensive than computes, right? That's why you have the cache hierarchy of in modern processors. So if you just think of this code, regardless of whether it's polyhedral or not, okay, the performance of this code is going to be bound by the available memory bandwidth. It's not going to be bound by how fast your processor can run, how fast it can compute, how fast this function foo can be evaluated, etc. Okay, that means such codes are called bandwidth bound or memory bound. Okay. Let's say that in each of these examples, the value that I wanted to return was just the last row of the table. Okay. In the second example, of course, it is updating row by row and is updating it in place. So the one-dimensional array B is going to be returned. Okay. So if you compare the first program and the second example, the first and the second example, they're actually computing something very, very similar. And in the first program, if I were only interested in the last row of A, then I could have written the program more efficiently. Okay. And this is related to a question that someone asked yesterday about what about the memory access and the memory access patterns and all that, right? So now I'm going to show you what we can do with that last example that we had. Okay. Remember the second example, we had this extra dependence that was based on the memory, and we chose this schedule then, right? All right. So I also told you yesterday that what is a good schedule, what is a good transformation, etc., is something that I am going to leave aside because it is too complicated to try and cover in just a superficial view. Okay. But I'm now going to give you an artificial metric. Okay. It's actually not very artificial, but it is in fact the first metric that people used. Suppose I want to find the fastest schedule. Okay. How many time steps does this have? 2n plus m. If I go from the top left to the bottom right along the left edge and go down and to the right, you can see my cursor, right? 1, 2, 1, 3, 5, 7. Because between every two rows, there are two timelines going. So the total number of time steps by the time I come here is 2n. Okay, and then I go to the right, and now at every point there is only one time step. So it is 2n plus m. This schedule that we had, and we figured out that it was the fastest schedule, right? Because we were figuring out the critical path of this graph. So this graph, the critical path length is 2n plus m. And in our first parallelization, if you remember, when the well, I don't have to go back. You remember the lines, they were 45-degree straight lines, right? Because the red dependence was not there. And so, in fact, those red lines were actually my timestamps, right? And with that program, the execution time was only n plus m. So it was significantly faster. If my execution time, assuming unbounded number of processors, is my cost metric, that first transformation and the first schedule is faster. Okay. I had two programs, one with a data space that was two-dimensional and the other with a data space that was one-dimensional. They were computing essentially the same thing, because the value that was computed depended on the north and the west neighbor. So I have two programs that compute the same thing, one that is memory efficient. So I start with program B, example 2, and I get a parallelization that has 2n plus m time steps. If I started with the memory inefficient program, I get a faster parallelization. And the second program does not have that fast parallelization because there is this red memory-based extra dependence. Because there's extra dependence, I have less flexibility on the schedule. I cannot go so fast in parallel. Okay? So the question is, can we do better? So I walked you through this way to through the process of how to generate the final program after choosing this 2i plus j as the timestamp. Okay. But what if we said the following? You know what? I'm going to analyze the first program and then I'm going to generate code that reuses memory, because I'm only interested in the last row of values computed by this program. Okay? And this is basically one of the things that make programming, polyhedral programming with equations, very attractive. I will not have time to talk about that. If you want, you can send me an email and I'll send you some links to some materials that argues that what you should really do is not write loop programs, but you should write mathematical equations that specify what is being computed. And these mathematical equations are really defining all the values that are computed. Okay? But if you find transformations for that, if you parallelize such a computation, then you end up with possibly inefficient code. And so the memory allocation can be chosen after you have chosen a good parallel schedule. Okay, so here is what you can do. I'm showing example 1 revisited is really, I want to compute example 2. Okay, so instead of doing this, okay, remember example 1 was basically from t equals 1 to n plus m minus a constant. Okay, and the loop body was aij. Okay, what if I change the loop body so that I am only using 2 rows? If you look at my picture for the first, this is good enough. Okay, when I compute any row, all that I'm using is the values in the previous row. The values from the rows above it can be overwritten. Okay, and so you can choose for program exercise 1 a memory allocation that, if you see, I have a two-dimensional array aij. I am going to map it. Just look at this code. Instead of aij, I say ai mod 2j. That's it. Okay, and I read from ai mod 2 and ai minus 1 mod 2. Okay, and basically the last if I am at the last iteration, I write this value of AI mod 2j into the output array B. That's all. So my program is only using 2n memory. And now I have the memory efficiency. I also have a faster parallelization. Okay. So I didn't have time yesterday to conclude with that, but that's basically an answer to the question that was asked, that in the polyhedral model, when you do these analyses, you can choose the parallel dimensions, you can choose the time, space, and memory dimensions. Okay. So I am going to stop here for a minute and ask you if you have other questions. Otherwise, I am going to talk about how to find these parallel wavefronts. Okay. So like I said, there are two issues: program transformation. How do you manipulate the program? How do you change it? How do you change the indices, etc.? And we saw that yesterday, right? And we saw how to interpret the transform equation, or so the equation is the program representation that we were working with. Okay. And we saw how to produce code at the end. And we also saw how, starting with a sequential program, you could deduce what the equations were. Okay. And I said I'm going to brush under the carpet how to choose the transformation. Today I'm going to tell you just a little bit about some part of the transformation. Okay. So I said that this transformation was a linear transformation. Okay. I am mapping this d-dimensional space I, j, k, l, all my indices, into another space which is also has the same number of dimensions. Okay. And so that mapping that I'm going to give you is defined by a square matrix plus possibly a translation. Are you with me so far? And I said that when I transform the code, I want the outer dimension to be time. Okay. That means the first row of this transformation matrix must be the coefficients of my schedule. Remember when I was showing you in the chat box the transformation that we were applied, our schedule was 1, 1, right? Because I plus j was the time step. And the other dimension that we chose was equal to I, right? And that became the transformation matrix 1, 1, 1, 0. Right? So let me, for a minute, go back and show you what I meant by that. If the transformation is, let me give a three-dimensional example, okay? Okay, here is a transformation that I'm applying. I just, out of the blue, I pick something. Ijk goes to I plus j, j plus k, k plus I. Okay? So this transformation is a mapping from three-dimensional space to three-dimensional space. In matrix notation, how would you write it? Yes?
1 1 1 0.
Yes?
0 1 1 and 1 0 1.
Okay, this 3 by 3 matrix is specifying this transformation. Okay, so let's say these were the I had done some analysis and I figured out that 110 is the timestamp. Okay. And the other dimensions are my processor dimensions. They are all parallel. Okay. So each row of this transformation matrix represents one plane or one family of hyperplanes. And I'm going to treat this 1, 1, 0 as the normal vector to a plane. If I have more than 3 dimensions, then it's a hyperplane. If it's 2 dimensions, then I have a family of straight lines. Okay. So when I figure out my transformation, I'm really going to figure out the transformation 1 dimension at a time, typically. Okay. And I said the outermost dimension has to be a time step. Okay. Now I want you to visualize this room or some 3-dimensional space. Okay. And look at the room that you're in. Okay. And look at the corner of that room. And imagine that's the origin. Okay. And think of the vector 1, 2, 1. Okay. That is the normal vector. And think of all the planes that are, the plane that is parallel to that, or a family of planes shifted by any constant. Okay. Go back, think about your linear algebra or your math, your math background. Okay. If the normal vector is 1, 2, 1, as I just gave you, all the points on a plane with this normal are of the form I plus 2j plus k equals constant. You agree? So this is the interpretation that I'm going to take for time steps. I want to sweep out my polyhedron with a family of wavefronts, okay? One after the other. When I choose when I develop the analysis for figuring out a linear schedule or an affine schedule, that is what I'm doing. Okay? The scheduling problem then is, as you just saw, figuring out what are the coefficients, what is the orientation of this hyperplane or these planes. Okay? So with that intuition, let's continue with the problem of how to find schedules. Okay? So I am going to sweep out my space with these planes. Okay? And in my program, I have dependencies. Right? I have vectors in my program that connect the consumer to the producer. Okay? So if I take the vector difference between consumer and producer, I construct the set of all the dependencies in my program. You agree? So if I go back to my picture that I had of our example 1, okay? And this is a somewhat tricky question. How many points are there in the iteration space? N squared, or n times m, right? There's a quadratic number of points. From each point, there is one vector that comes to the producer, or there are 2 vectors, right? Except at the boundaries. So there are roughly 2 n's or times m dependencies in the program. All right. However, if I talk about the set of vectors of the form consumer minus producer, there are only 2, 0, 1 and 1, 0, or 0, minus 1 and minus 1, 0, right? Because that same vector is replicated throughout the iteration space, and that is the kind of dependencies that particular program had, right? So this is again a very nice property of this program, and in general polyhedral programs have that property, have a similar property, and that is that there is a compact representation of all the dependence vectors that arise in the program. Okay? Now comes the crucial condition of scheduling. The condition is the following. Okay? That the timestamp of every consumer must be strictly greater than the timestamp of its producers. And this constraint must hold at all points in the domain. Okay? So we talked about this. We use the compact information in the program. Okay? So I am going to look at timestamps that are specified by linear coefficients like lambda 1, x1 plus lambda 2, x2 all the way. So here on the lowercase n is the number of dimensions. Okay. Okay. Like I said, the geometric interpretation is that all points that are executed at t equals lambda z plus u belong to an isotemporal plane whose normal vector is lambda. These are the scheduling coefficients that I'm seeking to find. Okay? All right. So here is the constraint. If you have a set of points, and for all points in that domain, some variable v depends on v of z plus d1, z plus d2, etc. I have s distinct dependence vectors, constant vectors, just like we had in our example 1 and 2 and 3. Well, not in 3. In 3, there was a complicated dependence, remember? But in examples 1 and 2, I have what are called uniform dependencies. So now I say lambda plus the constant alpha is a valid schedule if and only if for each of the dependencies and for all points in the domain, the timestamp of every consumer is strictly greater than the timestamp of the producer. Okay? Now here is the beauty of the polyhedral model. Because the schedules that we are trying to find are linear functions, and because we have uniform dependencies, let's just do a little bit of algebra. Lambda z or lambda z plus alpha is strictly greater than lambda z plus d plus alpha. Remember, d is a constant vector. Do apply distributivity and you find that the z and the alpha cancels out. Okay? And all you are left with is lambda dk is less than 0. The dot product of the schedule vector and the dependence vector, which is a constant vector, must be negative. Right? You have a hyperplane that defines a schedule. Its normal vector is this, and you have dependencies like this. I think the camera is capturing my fingers, right? Yes?
It's showing the slides, sir. It's
I'm
showing
showing
the...
Okay. Okay.
Yeah, we could see your fingers, the angle
So
you
here
were
is the
showing.
hyperplane, here is its normal
Yeah.
vector coming out. Okay. And the constraint is basically that all these dependence vectors, there are only a finitely many of them. All those dependence vectors have a negative dot product with lambda. Okay. Why? Because whatever I need must be scheduled at a strictly preceding time step. That's all. Okay. So this constraint is really defining the feasible space, or this set of constraints for all the dependencies that you have in the program, that is defining the feasible space of all legal schedules. And if the feasible space is the set, so now you want to treat the coefficients of lambda as the unknowns, and the dependence vectors d are parts that are constant vectors that you have deduced from the program and its dependencies. Okay? Now, That feasible space of legal schedules is the feasible space, it's basically a linear programming problem. I have not given you an objective function, but you can formulate, let's say I want to minimize the total execution time. Okay, remember that is not necessarily the best objective function that you can use. Okay, and there are many papers that explore this problem, and we have a decent answer for it now. But the point is, the feasible space of legal schedules is the set of coefficients that satisfy some linear inequalities. It is also a polyhedron. In fact, it is what is called a cone. It's a very special kind of polyhedron. Okay? All right. So I'm going to gloss over some of the details, but that is how you solve the scheduling problem. Or choose hyperplanes so that all dependencies point backwards. Okay?